Good morning, everyone. Thanks for joining us this morning for this webinar on building a scheduler using time and date functions. So the presentation itself is slightly longer than the last couple of weeks. It's around the 25-minute mark. And if we have any questions at the end, as usual, we can get to those. You can put them at any point. So let's not waste any more time. Let's get started.
Hello and welcome to today's webinar. Today we're going to be looking at building a scheduler using time and date functions. Let's get started. We'll look at what compare functions are, and we'll do a quick review of the OCS real-time clock. Then we'll talk about what a scheduler function is and what are some of the key components of one. There will be demonstrations throughout, and we'll finish with a Q&A session. Time and date compare functions are native instructions in Cscape, which are used to compare the current OCS real-time clock value with some preset set points. They're often used in applications like lighting control, building automation, and others where time and date are a key component of the control strategy. There are 5 time and date compare functions available, and you can find them in the time and date operation section of the project toolbox. There's time of day, days of week, months of year, days of month, and year. Compare functions are configured with specific criteria, such as time or date ranges. When the configured criteria of a function block, whether through a variable or a fixed configuration, match, the function block allows the power flow to pass. By connecting multiple function blocks, you can establish more precise time and date criteria to control specific outputs or machine functions. Now we'll look at the individual function blocks, starting with the time of day function. This function allows you to define a start time and an end time in 24-hour format. You have the option to either hard code the times, as shown on the screen, or assign variables or registers to the start and end times. This flexibility allows for dynamic adjustment of the times, whether through the touchscreen or other means within the application. Next, we'll look at the days of week function block. Each of the 7 days of the week is associated with a bit in a 16-bit variable, utilizing the lower 7 bits. To enable power flow on specific days, you simply turn on the corresponding bits in the variable assigned to the function block. Alternatively, you can also hard code the days of the week directly without using a variable or register. This flexibility applies to all the function blocks we're discussing. Now we'll discuss the month of the year function block. Similar to the day of the week function, each month is associated with a bit in a 16-bit variable, utilizing the lower 12 bits. To enable power flow for specific months, you simply turn on the corresponding bits in the variable assigned to the function block. Now we'll discuss the days of the month function block. Similarly, each day of the month is associated with a bit in a variable. However, due to the potential 31 days in a month, a double integer variable is required for this function. To enable power flow on specific days of the month, you set the corresponding bits in the assigned variable. Lastly, we'll look at the year function block. Similar to the days of the month function, the year function also requires a double integer variable for assignment unless hard-coded. The lower 16 bits represent the start year, while the upper 16 bits represent the end year. Alternatively, you can directly hard-code the start and end years as you can with all these variables. Now we'll review the real-time calendar clock capability in the OCS. The OCS incorporates a real-time clock, or RTC, through a set of dedicated system registers. These registers include second, minute, hour, date, month, year, and day. The values in these registers are encoded according to the specified format as shown on the screen. Now we'll look at another useful feature in the OCS for project development, the time and date graphical object. In the graphic editor, you'll find the icon for the time and date graphical object, highlighted among the list of icons at the top of the screen. This object allows you to display either the time or the date with various formatting options to choose from. You can customize the display to show seconds or minutes and configure different date formats such as 2-digit or 4-digit year with the option to display the date before or after the month. When assigning a variable to a time display, you should reference SR44, which corresponds to the real-time clock second register. On the other hand, if you want to display the date, you'll reference SR47, which corresponds to the RTC date register. These system registers provide the necessary data for the time and date graphical object. Now we'll see the time and date functions in action using Cscape. In the toolbox, you'll find the 5 functions we discussed earlier under time and date operations. We'll look at them now. We'll double click on the time of day function block. In this demonstration, we have hard-coded the start time as 7:30 a.m. and the end time as 7:30 p.m. in military or 24-hour format. Now, let's say we have a scenario where we have an output that is only going to be on certain days of the week. So it has a time schedule, but it's only on certain days of the week. In that case, we can add the day of the week function to the string of function blocks for time and date compare. So again, we've hard-coded function block, but as you can see, we've designated that Monday through Friday will pass power flow. That's a Monday through Friday in the Western world operation. In different countries, there would be different days in which businesses are typically closed. It's not always Monday through Friday, but that's what we've shown in this particular example. Now we'll have a demonstration of isolating a particular date. In this example, we'll focus on New Year's Day, or January 1st. Here's how it works. Start by setting the range of years between 2023 and 2099. This allows us to cover multiple years for the New Year's holiday. Next, we'll pass power flow based on the specific month, which in this case is strictly January. Finally, we'll narrow it down to the first day of the month, January 1st. By combining these conditions, we can flag a coil that represents the New Year's holiday. This approach is useful for fixed date events that don't change from year to year. During debugging, we can analyze the behavior of this scenario and observe the power flow as it aligns with the designated conditions. Both Zone 1 and Zone 2 outputs should be active. It's after 7:30 a.m. and before 7:30 p.m., satisfying the time of day condition. As it's Thursday, the day of the week condition for Monday through Friday also applies, allowing power flow. However, since it's not January 1st, the New Year's holiday bit remains inactive. So that's a look at the time and date compare functions. Now we'll look at the scheduler function and understand its purpose in control systems. A scheduler function is utilized to define time and date parameters for controlling various aspects, whether it's an individual output, such as a light or a heater, or even an entire machine function. While schedulers are commonly employed in building automation and lighting control, their applications extend beyond these industries. They can also be beneficial in machine control scenarios. For instance, if you needed to warm up an oven before commencing production. In this case, a scheduler function would prove invaluable. As you can see, schedulers have a wide range of applications across different industries. Now we'll look at the key components of an effective scheduler design. Firstly, the ability to set the desired type of operation or time-based schedule is crucial. This includes options like daily schedules, where the device operates every day of the year, or weekly schedules, where it runs on specific days of the week. For weekly schedules, it is important to have the flexibility to specify the desired operating days. Additionally, setting the hours of operation is essential for devices that do not run continuously. Handling exceptions is another vital aspect, which involves accounting for special dates or holidays when the system may not be operational. Lastly, having the capability to override the controls is necessary for situations where manual intervention or adjustments are required, such as during unexpected production delays. It is important to consider how these components are integrated within the scheduler and the overall control scheme to ensure effective operation. Now we'll look at a demonstration of a scheduler that we have prepared. We have a simple main menu featuring a 4-zone scheduler. The menu options include zone configuration, holiday configuration, and a clock setting function. Now we'll look into each of these components to understand their functionality. We'll begin by exploring the set clock function. In Cscape, you have the option to create your own set clock screen or use the built-in set time and date menu item available in the system menu. For this demonstration, we opted to utilize the existing menu. When the set clock button is pressed, it immediately navigates to the system menu section where the real-time clock and date can be set. This eliminates the need to create a separate screen and simplifies the user experience. The system registers include a pre-created sysreg variable that displays the current system menu screen number. By monitoring this variable, we can identify the screen number associated with the time and date menu area and program logic to navigate to that screen when the button is pressed. After making the desired changes, pressing the escape key returns the user to their previous location. This feature offers convenience and ease of use for configuring the time and date settings. Here we have a 4-zone system where we can assign names to each zone for easy identification. For the first zone, we named it Offices using an ASCII field. We have a selector for choosing between daily and weekly operations. Daily operation means the zone operates at the same time every day, while weekly operation allows for specific days of the week. Start and end times are set separately for hours and minutes, as the time and date compare blocks handle them as individual variables. To facilitate this, we've created separate data fields on the screen. The push buttons, acting as toggle switches, are connected to individual bits within a register or variable that manages the days of the week. Additionally, there is a toggle option to enable or disable the zone's adherence to a holiday schedule. In this case, I've set the flag to yes. An indicator displays the current status of the output, and there is also an indicator showing the current time and date. The only feature not currently incorporated is an override function. It would be beneficial to include an override button to display the zone schedule or manually override the output. However, this can also be handled outside of the scheduler as a separate application requirement. Zone 1 is configured for the offices, operating from 7 am to 7 pm. Zone 2 is set for the production area, operating weekly from Monday to Friday between 6:30 am and 11:30 pm. Zone 3 is set as loading dock and configured between the hours of 5 am and 10 pm. Zone 4 is currently unconfigured and we'll set it up now. We'll name this zone Grounds, primarily for outdoor lighting purposes. We'll use the ASCII keypad to input the name. For the ground zone, we'll keep it on a daily schedule, which is the default, without any holiday considerations. We'll set the lights to turn on at 7 pm and off at 7 am. This means the lights will be active from 7 pm to 7 am. It is important to note that for outdoor applications, additional features like daylight sensors or adjustments for varying sunlight levels based on location and time of year can be incorporated. However, for this demonstration, we are keeping it relatively simple with zone control. Now we'll go back to the home menu and we'll look at configuring holidays, which enhances the usefulness of a scheduler. Although it's not mandatory, holidays are significant events to consider. In this setup, we have included the ability to configure up to 16 holidays. Users can navigate between holiday numbers from 1 to 16. We'll start with holiday number 1. The order of holidays doesn't matter. It's just a way to add the observed holidays for a specific business or organisation. For our demonstration, we'll start with a fixed holiday that occurs every year on January 1st, which is New Year's Day. Regardless of the year, January 1st will always be a holiday. If we had a floating holiday, we would set it for a specific year. We'll cover floating holidays shortly. After configuring the parameters and naming the holiday, it's crucial to remember to store it. Although we haven't made any changes, we'll press the Store button to reinforce the concept. The next holiday we'll configure is Good Friday. The date of this holiday changes every year, which makes it a floating holiday. This year, it falls on April 7th, so that's what we set it as here. For floating holidays, the date needs to be updated yearly. Next, we'll look at the Cscape program for the scheduler we just discussed. To begin, I'll guide you through the hardware configuration. If you have access to the internet or a local server in your plant with an NTP server, you can ensure accurate timekeeping on the OCS. In this application, we've set up a gateway and specified a DNS server. In this demo, we're using time.nist.gov as the server to regularly update the OCS's real-time clock with the correct time. This approach guarantees precise timekeeping as the OCS periodically checks and updates its clock. The frequency of checks is designed to avoid any issues caused by excessive pinging. Remember, you can also utilize an internal time server within your plant, eliminating the need to connect to external networks. This tip provides a helpful suggestion to optimize time synchronization for your schedule. Now we'll look at how we organized this program. In the main loop modules, there's no activity in the main section. It's left empty for individual customization. Each zone has its own logic section, which is relatively simple. You can choose between daily control or weekly control for each zone. With daily control, the output is determined solely by the time of day, regardless of the day of the week or holidays. This is suitable for zones like the outdoor area. Although holidays aren't incorporated yet, we'll explain where they fit in later. In Zone 1, we have both daily and weekly operations, where the day of the week becomes relevant. Below, we have straightforward logic stating that if either the daily or weekly output is activated, the zone output should be turned on. The holiday flag determines if the zone is affected by holidays. If the flag is not set, holidays have no impact on the output. However, if the flag is on, the output will be prevented from turning on holidays. If it's not a holiday, the output can pass power flow. This logic is identical for all four zones. Overrides haven't been incorporated in this program, so handling overrides separately would be necessary. Overall, the zone control is straightforward. Now we'll look at the screens for zone control. We'll focus on Zone 1 for this part of the demonstration. Here we have a fixed byte array for the zone name consisting of 10 elements or 20 characters. The 16-bit selector determines whether it's a weekly or daily schedule with values of 0 or 1. The start time and end time variables are used in the function blocks. The holiday flag indicates if the zone is affected by holidays. The day of the week is represented by individual bits within the zone register. The lower 7 bits correspond to Sunday, day 1 through Saturday, day 7. Time and date objects display the current time and date, and the day of the week is shown using a text table. Additionally, there's a bit indicating if it's a holiday today, which will be explained later. This covers the basic zone control logic. Now we'll proceed to the more advanced holiday control and navigate to the holiday configuration screen. Now we'll look at how we've set up the holiday configuration. We have multiple arrays, each with a dimension of 16. These arrays include names, start years, months, and dates. They all correspond to the 16 different elements in the array. Now here's how it works. The 0 element in each array is used to display a holiday that can be edited on the screen. However, only holidays 1 through 15 can actually be saved. So even though we mentioned 16 holidays, it's actually 15 holidays that are supported. When the user manipulates the data on the screen, the changes made to the 0 array data are copied to the corresponding indexed array. For example, if the user is editing holiday number 7, they are actually editing the 0 array data. When they hit the store button, the data from index 0 is copied to index 7. It may sound a bit complex, but it's a clever way to manage the holiday configuration. Now we'll walk through the code for this scheduler demo. The code is well documented, so we won't spend too much time on it. First, we have a subroutine that is called every day at midnight to check if it's a holiday. This subroutine, called holiday today, runs through a loop to compare today's date with the stored holiday data. If a match is found, a flag is set to indicate that it's a holiday. Once the loop completes, the subroutine returns to the holiday section. This is how we determine if today is a holiday or not. We also have logic for displaying holiday data on the screen. Depending on the selected holiday number, the corresponding start year, month, day, and date data is loaded into index 0 for display. The operator can then make modifications, and when they press Store button, the modified data in index 0 is moved to the previously selected index number and stored. Additionally, we have a set time routine that we mentioned earlier during the bench demo. When the Set Time button is pressed on the screen, it loads a value of 10 into the system register, which takes the user to the time and date screen. Cscape incorporates built-in time and date compare functions, eliminating the need for custom function blocks. These functions are valuable for real-time clock-based control and scheduler implementation. A scheduler should be capable of managing time and date parameters, allowing for daily or weekly operations. It should also handle exceptions, such as holidays, and potentially accommodate manual overrides. While manual overrides may fall outside the scheduler's scope, they should still be addressed in the overall system. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, not seeing anything currently in that. If anyone does wish to have that demo program, you can just make contact with tech support and I will send it out to you. Okay, so Netweeks we have Modbus variable conversion using enhanced IEC. So it is slightly different to what you're used to with the standard stuff. Okay, on that note, I think we'll leave it there. Thank you all for joining this morning, and we hope to see you again next week. Have a good day.